So when doing springs, the spring force rules actually has a name for the guy who came up with all of it. The guy's name was Hooke. He did a whole bunch of cool science stuff in our, scientific resolution time, Newton's time, those kinds of things. Hooke's law is just the force formula for springs. So the force of a spring is equal to minus kx. That's the spring force law. You guys know your spring force law. So spring force exerts an oppositely directed force. Oppositely. I gotta spell. Oppositely is not the easiest word to spell. And it's equal in magnitude to the applied force trying to crush the spring. Now, the applied force trying to compress the spring, I can just say Fp is equal to Kx because that's the same direction force. That force is pushing in the direction of the compression. The spring force tries to resist it. And basically, this is just an example of Newton's third law, where if you push on something, it will push back, right? Anytime you push on something, it pushes back, which is the main difference with springs. That's why that negative exists in the formula, is because it's the other direction. That's why it exists. The spring constant is a measure of what? What's a spring constant, that K number? What does it mean? Ooh, yeah.
How hard is the pressing?
Yes. So I'm going to call that in one word, stiffness. So a really, really high K means it's really hard to compress. If it's a really, really soft spring, it's got a really low K. Yes? Because I'm looking at you, looking down, writing at Lou, looking at you, back and forth, up and down. Here, let me clean that up. Erase button. There we go. Nice and pretty now. Does anyone remember what the unit of a K is? What is K measured in? Newtons per meter. So not a Newton meter, Newtons per meter. Newton meter is a completely different thing. A Newton meter is what? We already talked about that. We did that in lesson 1. Newton meter is a joule. It's an energy. That's it. That's it for the first bit. We were all familiar with this picture. I think on your printout it looks pretty bad. But basically this is a picture of pulling on the string, or pulling on the spring, and it pulls it back a bit. So the force is in the other direction. This is normal. And then if you push on a spring, the force is backwards. So it's just showing you, it's kind of small. It's in your textbook too. It's just back and forth of the spring. It's the same picture that I used in the spring force lesson from the last chapter. Okay. Back to the new stuff. Okay, new thing is the energy stored in a spring when you compress it beyond its normal length. So if you compress a spring, you're giving it energy, and if you stretch a spring, you're also giving it energy. And it has this formula. The energy in a spring is equal to half of the K times the x squared. That's the formula for the spring energy. So that's how much energy is stored in a spring. Very easy to memorize because it looks almost the same as the kinetic energy formula as far as style. It's your half mv squared and your half kx squared. So on the formula sheet, that's all. Now work is also equal to the area under the curve. Of force versus displacement. And I have this little chunk here to draw my little graph. It's going to look like this. I'm going to draw a line that does this. And this is my force pushing in on a spring, and this is X, how much that spring is compressed. And the work here is all of the area underneath it. So that's going to look like this. that actually ended up looking pretty good. Back to normal. Okay, so work done. So we're going to talk about work because this is our chapter on work. Work done to compress a spring is equal to the change in elastic potential energy. So basically that is our main trade in this chapter. We're going to say how much work was done on the spring. Well, how much potential energy did I give the spring? That's our trade. So the way we write that is say the work done to compress the spring is equal to the change in energy of the spring. And we're going to do a long way of writing this. We're going to say that's half of kx final squared minus half of kx initial squared. So that's a long way of saying it's just the difference between the beginning and ending state of your spring. So I like the way to write this like with all the halves and the k's in there. I can factor out the half and the k, but that usually makes the algebra more confusing. Because now I have the after energy minus the before energy is the change in energy. So that's kind of where I've written it there. And we know that the K doesn't change, right? Doesn't matter how much I compress the spring, the stiffness of that spring doesn't change. What is changing is the how much compression, right? More compression, more force. All right. It's kind of weird. Now, what's even more annoying is the opposite effect. So the work done by the spring, spring, is equal to the negative of that same force. So the work done by the spring is equal to negative the work done by the push on the spring, right? That's just That's just Newton's third law, in and out. And that's our conservation of energy. Remember, work is energy. So the in work has to equal the out work. That's always true. And then this would be negative the change in elastic energy. Now, I'm not going to write this again. But what would change about this one and this one? It would just be flipped. You do the subtraction of the initial first and the final second. You just flip it. So I'm not going to write it all out because I don't have space. But hopefully that's good so far. The main reason why I'm saying all these things, and it's a whole lesson in itself, is if there's elastic potential energy in a problem, such as a spring launching an object with a speed, that is now part of our total mechanical energy. So this is included in the total mechanical energy. We can do our E, keep trying to write them backwards. It's E total is equal to all the kinetic energy it has plus all the potential energy it has, now also plus all this spring energy it has. So we're just adding a list of energies to our total here. So we have all the kinetic, all the potential, and all the spring. So if it's up high, it has potential energy. If it's moving fast, it has kinetic energy. And if the spring has changed its X, then the spring has energy too. We add all of those effects together to be able to solve problems. So what we're going to be able to do here is we have a spring constant K and another spring constant K. So here's our diagram. I've got one spring stuck to another spring. They're two different kinds of spring. They are either thicker or made of different materials. One is a lot stiffer than the other. Now, annoyingly, what I want the constant of this combination of springs together, the really annoying thing is it's not 40. right? That would be really easy and not worth me asking this question as a part of a lesson if it was 40. And I'm hopefully going to try to explain the reason here. So what I'm going to try to do to try to explain why it's not 40 is I'm going to basically zoom in to the middle. So I know they're connected to each other, but I'm just going to zoom and look at the forces like there's a lot of space between them so I can draw my forces a little easier. So I'm going to draw this here. I'm going to have the center here. And then one string will pull in one way and one will pull the other way. So we have one force of spring and then the other force of spring, right? So the forces of spring are what's exactly the same, right? Because if you pull on the spring, the transfer between those two parts is going to be equal. So what's the same in both of these? It's Newton's third law. The force on each is the same, right? So that's what's going to be equal. So these two forces are equal. These two forces that we're going on is equal. And we're going to say the force of spring A and B. Now, the way I wrote this in, so I follow the notes ahead of time, let's see what I can see here. What's the A is 16 and the B, that's A and that's B in this case. So A is 16 and B is the 24. Just the way we wrote this. So that one's A here, this was B here. So we're going to do our equations, lots of equations. We know the FP is equal to KX. And so we have two different rearrangements to do. We have we're going to do here. We're going to do X is equal to FP over KA, and XB is equal to FP over KB. Right? Okay. No, part B says I pulled it out with 4.8 newtons. It's one step. We have F is equal to KX. And so I want to know how far X is equal to F over K. And I know F, it's in the question. I know K. I just did a whole bunch of math to find it. One division, we're done. So the force, 4.8 newtons of force. The new K, 9.6 newtons per meter. And notice we're going to get our newtons divided by newtons per meter. Meter is what comes out of this fraction. And so this is just half, right? 0.50 meters. Nailed it. We did it.